Good morning, ladies and gentlemen. We are running this lecture in a recorded mode, so I will publish it and you will see it in Moodle. You are more than welcome to ask any questions actually on the topic of the lecture later on in Telegram and obviously also in practical sessions, and please just clarify any points which may remain unclear. So today we are continuing on the topic we started last time. You'll hopefully see my screen. You remember that we started last time studying linear transforms of coordinates, and in doing so we introduced the notion of matrices as a compact form for representing linear transforms, and matrix to vector multiplication, which would allow us to express old coordinates via the new one, or possibly new via the old. So we came very close to the notion of composition of linear transforms and matrix multiplication. That's what we would like to explore today. So starting with composition of transforms. And using the notion of matrix multiplication to express them. Okay, as we did at the end of the last lecture, we again consider 2D example, for the moment 2D only, and with that, we would consider two transforms, two rotations initially, one of them at the angle alpha, as we did, and then relative to that would consider yet another rotation at the angle beta, which is a very simple example. Nevertheless, it allows us to introduce the notion of matrix multiplication easily. So xy is the very original coordinate system. Now we have another one, which we'll call x prime y prime, which is obtained by a rotation at the angle alpha. Positive alpha corresponds to counterclockwise rotation, as we discussed last time. And so that's a new coordinate frame. Now we would introduce yet another coordinate frame, which I denote by x double prime, and therefore y double prime, which is obtained from x prime y prime by a rotation at another angle beta. If you remember, we would use the notations for brevity of xi prime and xi double prime of vectors expressed in the corresponding coordinate system, x, y, x prime, y prime, and x prime, y double prime. And then the connection between these two systems, three systems actually, would be the following. So first of all, a vector xi is matrix, let me denote it by matrix A times xi prime, where matrix A, you remember we introduced it, it is cosine alpha minus sine alpha, sine alpha, cosine alpha. Similarly, obviously, xi prime is some matrix B times xi double prime, in a very similar way, where B is composed of the angle beta, which denotes a relative rotation of xi double prime relative to xi double prime y double prime relative to xi prime y prime. So it is exactly of the same form, cosine beta minus sinus beta, sine beta, cosine beta. Okay, so let us now express directly psi via psi double prime. Well, we already know using our matrix notation. So if in general we denote our matrix A to be a matrix of elements A, I, J. So for example, A11 is cosine alpha and so on. A22 is cosine alpha as well. And our matrix B is similarly denoted by its element B, ij, where obviously B11 is cosine beta, and so on. B22 is cosine beta as well. Then we know through our matrix by vector multiplication that psi I is a sum. Obviously, matrices are two-dimensional, so n is equal to 2, but we'll do it in the general with the general notation. So it is a sum from j equals to 1 to n, a I j psi prime j, and psi prime, in this case I can say without any loss of generality, I can use any letter for the index. Let's say psi prime j equals to sum, but in this case I cannot use j here, so the running index must be a different letter than the free index, which is in the left hand side. So I would use k from 1 to n, b j k psi double prime k, and therefore let me express psi I directly. So psi I would be sum from j1 to n, a I j, sum from k 1 to n, b j k psi double prime k. What I now want is to change the order of summation. Obviously, we can do it because addition is commutative. So, changing the order, I would get sum from k1 to n, sum from by j from 1 to n, aij, bj, k, psi double prime k. Now, let us look at this element in the middle. So this is a certain sum which depends on k, because there is an outer summation with respect to k, where j is a running dummy index in this case. So this entry depends on I, which is in aij the same as in the left hand side, and it depends on k, whereas j is a dummy running index. So this entry can be denoted by c I k, and in that case I can say that it is a sum of over k from 1 to n c I k times xi double prime k, and we achieved our objective of expressing xi directly through xi double prime. So this is again nothing else. This is again a matrix by vector multiplication. So Cik would be elements of matrix C, a certain matrix C, we'll see which, with elements C11, C12, C21, and C22, where Ci, for example, K, well, I can write it that way to be clear. Cik, as we said, it is sum from j1 to n, aij, bjk. But I'm absolutely free to use different letters for free indices and for dummy running indices in the sum, provided that they do not clash. So the dummy running indices and the free indices must be denoted by different letters. So I can, for example, swap the notations of k and j in this case, and equally I can write, for simplicity, Cij would be sum from, but now we're using k for the running index, k1 to n, ai now k, b, k, j. What is this? This is precisely the rule for matrix multiplication. Matrix multiplication. Why? As we wrote that in matrix notation, psi was A, matrix A times psi prime. Psi prime was matrix B, psi double prime. And therefore we could write psi equals to A times B psi prime. This is perfectly okay in terms of matrix by vector multiplication, because we already know that b times psi prime is another vector, and then a is multiplied by this vector. But now we can really write it as a times b using matrix multiplication times psi prime, where a times b is precisely our matrix C, and this matrix C is defined using this rule, which I put here. So we have defined matrix multiplication. A times B is another matrix C, where entries of matrix C are given by this rule. Please note, this is a very interesting thing, that in this case, unlike x plus y, a plus b, unlike a plus b, matrix multiplication AB is not component-wise. It is a much more complex thing. Well, so if we write our matrix A, A11, A12, A21, A22. This is our matrix A. And we multiply it by matrix B, which is B11, B12, B21, B22. So what happens? This formula denotes the element of row I, that's row I, and column J in the resulting matrix C. So that's B, that's C. How are they obtained? So you see, we take all elements of the corresponding row of matrix A, for example, the first one, and we multiply it by the corresponding column elements. For example, J is 1, and then K is running from 1 to n. Therefore, we're going along the column of matrix B. So the first element of our matrix C is going to be A11, B11, plus A12, B21, B21 in this case. The second element would be, we're taking first row, second column. We're taking okay, first row, second column. In this case, we're taking first row of our matrix A, but we're now taking the second row of second column of our matrix B. So it would be A11 times B12 plus A12 times B22. Okay. Now, to get the second row elements of matrix C, we take the second row of A and then first and second column of B. So, first of all, second row of A by first column of B. A21, B11 plus A22, B21. And finally, last row of A by last row of B. A21, B12 plus A22, B22. So matrix multiplication is, remember, column, row by column, row by column, row by column. From the first matrix, which is on the left-hand side of multiplication, we take rows. From the second one, we take columns, which immediately suggests that matrix multiplication defined this way is non-commutative. Matrix multiplication is not commutative. This is the first and the best well-known example of non-commutative multiplication. Matrices do not commute, which means that A times B in general is not the same as B times A. And from the above rule, it is quite easy to understand why. Because the multiplication is defined in such a way that from the matrix on the left-hand side, we take rows. In the matrix on the right-hand side of multiplication, in the second multiple, we take columns. And that's why this operation is asymmetrical. You can very easily see for yourself, take just some arbitrary matrix A and matrix B, multiply A by B, and then multiply B by A. swapping the order, and you will see that the results are indeed different. This is a very, very, very critical point to remember. On the other hand, matrix multiplication is still associative. You can prove by direct expansion of the formulas we have seen that A times B times C for any matrices, currently we're considering square matrices of n by n size, is same as A times B times C. That's true. You can also prove using the same formula which defines matrix multiplication, this row by column formula. You can also prove that there is a distribution law in matrix multiplication. A plus B times C is the same as A times C plus B times C. Okay. Furthermore, let us see the geometric meaning of matrix multiplication we have defined. So as we pointed out, this is a composition of linear transforms. So if the first linear transform was given by A, the second one by B, the composition is given by A times B. So in this particular case, let us compute this A times B. So you remember that A was cosine alpha minus sine alpha, sine alpha, cosine alpha, and B was cosine beta minus sine beta, sine beta, cosine beta. Okay? So what is A times B in this case? A times B, let us compute it. And you remember that A times B in this case gives us directly our vector, the very old one, xi, via xi double prime. So first row by first column, cos alpha cosine beta minus sine alpha sine beta, minus sine alpha sine beta. Great. First row by second column, cosine alpha minus sine beta, cosine alpha minus sine beta, minus sine alpha cosine beta, minus sine alpha cosine beta. Okay. Second row by first column, sine alpha cosine beta plus cosine alpha sine beta. And finally, last row, second row by second column, minus sine alpha sine beta plus cosine alpha cosine beta. but then using the very elementary trigonometric properties of sine and cosine functions, we can collapse this to what is this? This is obviously cosine of alpha plus beta. What is this? This is minus sine of alpha plus beta. What is this? This is sine alpha plus beta. And the final entry is again cosine, cosine minus sine, sine, which is a cosine of alpha plus beta. So we got this matrix C, which corresponds to, in fact, as we know, if A was a rotation at alpha, B was a rotation at beta, then C is a rotation. It has exactly the same structure, cosine, sine, sine, cosine, rotation at the angle alpha plus beta. And of course, this is true. This must be true. This is not surprise at all because of the way of how we constructed our transforms. So if we look at our original drawing, then indeed the coordinate frame x double prime, y double prime is rotated relative to xy at the total angle, yes, which is alpha plus beta. So of course, defining our rotation via a matrix form and then introducing matrix multiplication to define the composition of our rotations, we must have arrived at a matrix product which corresponds to a rotation at the sum of the angles, alpha plus beta. So, which confirms that our matrix multiplication is done correctly in this case. So, great. Let me introduce a very important notion. You will see its importance later when we start defining, first of all, methods of solving linear equations and also the notions of linear dependency and independence of vectors. This is the subject of the next lecture. I am talking about the notion of the determinant. So for the matrix A, which is in general, let's say A11, A12, A21, A22, the determinant of A, or we sometimes would use the notation like absolute value of A. Obviously, the absolute value of a number is defined, as we know, from the elementary mathematics. The absolute value of a matrix is not an absolute value of, is not a matrix of absolute values of its elements. It's a determinant. It is a single number, actually. So it is defined for a 2 by 2 matrix in a very simple way. It is the main diagonal minus the second diagonal. So it is defined in a way as A11, A22 minus A12, A21. Why this? This definition has its origin in solving systems of linear equations. So let's consider again a system of our linear equations. In general, we will say, for example, x prime 1, let's say the other way around, to be consistent, x1 equals to a11 x prime 1 plus a12 x y prime, sorry, we'll use x1 better. So x equals to x prime plus a12 1 prime, okay, and y equals to a21 x prime plus a22 y prime. Suppose this. Or we can use, obviously, notation xi1 for x, xi2 for y, and xi prime 1 for x prime, and xi prime 2 for y prime. Here I choose using x and y instead of xi's. Doesn't matter. So we're solving this system of linear equations, a very elementary one, with respect to x prime and y prime. So again, what do? We do elimination, all right? In order to express x prime, we want to eliminate y prime from the system. So we multiply the first row by a22. We multiply the second row by minus a12. And therefore, when we add them up, we get y prime eliminated from the system. And therefore, we get a22x equals to a11 a22x prime a22x plus sorry, minus a22x minus a12y equals to a11 a22x prime minus a12 a21 x prime, and therefore x prime times a11 a22 minus a12 a21 equals to a22x minus a22x minus a minus a12y. And this allows us to express x prime, provided that, of course, this coefficient is not 0. So in that case, x prime is simply a22x minus a12y divided by this quantity a11 a22 minus a12 a21. This is precisely, the denominator is precisely the determinant of A. And in a very similar way, you can do it for yourself. We can express the y prime variable, in which case we again have this determinant of A in the denominator. So we can conclude from this very simple example that our very simple 2 by 2 linear system is solvable and indeed has a unique solution with respect to x prime, y prime, So solution exists if the determinant of A is not equal to 0. So this condition that determinant of A is not equal to 0 is sufficient for the solution to exist. Sufficient condition. Why it is not necessary? You can see that it might be that, for example, our determinant is equal to 0, and nevertheless, the numerator in this formula is equal to 0 as well. In that case, solutions for x prime, for example, would still exist, but in that case, a solution would not be unique. This is a degenerate case. We'll deal with those degenerate cases and cases of linear dependency later. For the moment, we would say that the determinant of A is not equal to 0 is a sufficient condition for solvability of a linear system. By linear system, I mean a system of linear equations. In general, if we have a system of equations like xi equals to A times xi prime, and now n is, let's say, any, then the sufficient condition for this system solvability would be the determinant of A is not equal to 0. But what is the determinant for an n by n general matrix? We will discuss this later, how the determinant can be computed for the general matrix n by n. For the moment, I will give you a formula for the determinant of a 3 by 3 matrix. We may need it in the future, and it is a very important thing to remember in general. For larger dimensions, like for example 4 by 4 and so on, then closed form formulas for a determinant are very, very difficult to remember. They become large, but using the rules which we will introduce later, you can compute these determinants very easily. So that may be deferred actually to the general linear algebra course, which you will have in the next term. For the moment, let me give you a formula for the determinant of a 3 by 3 matrix. How do we get it? In exactly similar way. So we consider a 3 by 3 system of equations, 3 equations and 3 unknowns, solve it explicitly by elimination of variables, so by multiplying rows of this matrix with such coefficient that we eventually zero out, and adding them up, zero out all coefficients but one, and that way we express solutions. And in the denominator of all those formulas would be, similar to the two-dimensional case, would be the determinant of our matrix A. So if our matrix A is 3 by 3, so it is A11, A12, A13, A21, A22, A23, and A31, A32, A33, suppose that, then the determinant of A is computed in the following way. We take the main diagonal. Remember the rule. First, take main diagonal The main diagonal always goes from the upper left corner to the lower right corner. So this is called the main diagonal of the matrix. Very similar to the main diagonal of our 2 by 2 matrix. Multiply the elements and take the product with a plus sign. So it is A11, A22, A33. Okay. Now we take secondary diagonals parallel to the main one. So we take this one and multiply, so again with plus, A12, A23, and multiply by this corner element A31. Now we take again plus another diagonal parallel to the main one, A21, A32, and multiply also it by another corner element, so forming these triangles, A13. Now that's not all. These are three positive taken with a plus sign products. Let me rewrite my matrix again in order not to confuse the notation for you. A12, A13, A21, A22, A23, A31, A32, A33. Now we take the opposite diagonal, going from the upper right corner to the lower left one, and this product goes with a minus. Minus A13, A22, A31. And now you can guess what we do. We take another secondary diagonal and form a triangle with A11 and take it with a minus. A23, A32, A11. And finally, we take this diagonal, secondary diagonal, and form a triangle with A33. So minus A12, A21, A33. So as you can see, that's all. As you can see, for a three-dimensional case, the formula for determinant of A is already quite complicated. Still, this rule is easy to remember, and I recommend that obviously for a 2 by 2 matrix, it is very, very easy to remember the rule for the determinant. It is slightly more complex for a 3 by 3, but you can remember it. For all other cases, we'll learn later how a matrix can be decomposed in such a way that its determinant can be computed by parts. So, what is the determinant for the rotation matrix? The rotation matrix, if you remember, our matrix A was cosine alpha minus sine alpha, cosine alpha, and therefore the determinant of A is obviously cosine minus sine. So it is cosine squared alpha minus sine squared alpha, which is equal to 1. And this is very important to remember. So for rotation, this is a rotation, the determinant is 1. Moreover, if we consider both actually rows and columns of our matrix A as vectors, so for example, consider the first column and the second column as vectors, and we compute the dot product of these vectors. The dot product of cosine alpha sine alpha. You remember, component-wise dot product, sine alpha cosine alpha, cosine minus sine plus sine cosine, which is 0. And in a similar way, if we consider a row vectors of our matrix A, so cosine minus sine, sine cosine, although written as rows, we consider them as vectors. Then again, cosine sine minus sine cosine, the dot product is 0. This is a so-called orthogonality property. So A is orthogonal. The dot product of rows and columns of this matrix is 0. The determinant is 1. And you can also see that the rows and columns are normalized. So the sum of squares of each row and each column is 1. Cosine alpha plus minus sine alpha both squared is 1. Sine alpha squared plus cosine alpha squared is 1. And in a similar way for both rows and columns. So what we can say is that for any I in general, sum of squares of the elements I1 to n, j 1 to n, aij squared is 1, which means that each row I is normalized to 0 to 1. Similarly, columns are normalized. So for any column j, if we now move along rows, sum from I1 to n, aij squared. Please notice a subtle difference between these two formulas. In the first one, I is a free symbol and therefore fixed, whereas j is running from 1 to n. In the second one, j is fixed and I is running from 1 to n. Nevertheless, sum is 1. Now we can say that for any ij, let's say a row such that I is not equal to j, the dot product of rows is 0, which means that sum from k1 to n, ai k a j k is 0. And in a similar way for any ij such that, so which means that a rows, so this means that each column j is normalized to 1. This one means that rows are orthogonal. And in a similar way, we can say that columns are orthogonal. So k1 to n, a now other way around, ki, we're moving along rows from 1 to n with the column I, and in a similar way column j, this is also 0. By the way, these orthogonality conditions, normalization and orthogonality conditions, they by themselves do not imply that the matrix has determinant equal to 1. So if we consider these conditions in isolation, it is possible to prove that the determinant is equal to, determinant of A is equal to, I'm not going to prove this, the proof is quite tedious. You can prove that the determinant of A, sorry, the determinant of A is equal to plus or minus 1. So the case of plus 1 we have already seen, but there is also a very important case of the determinant being equal to minus 1. And it has a perfect geometric meaning as well. So let's discover that geometric meaning in a 2 by 2 case. So determinant of A equals to minus 1. What does it mean? Consider a very simple example. X equals to x prime, y equals to minus y prime. So let us, so on the left hand side it is a vector xi, in the right hand side it is a vector xi prime. Let us express this in terms of a matrix notation. So xi equals to what? Times xi prime. X depends only on x prime, therefore the first row is 1, 0. Y is minus y prime. So the second row is 0, minus 1. So it is a matrix which is 1, 0, 0, minus 1. That's our matrix A. And according to the formula for the determinant, we indeed see that the determinant of A is minus 1. This transformation geometrically is not a rotation. This is a symmetry. You see that x is the same, so this is x and y, and x prime is the same as x, but y prime is different with y by a sign. Therefore, y prime is pointing into the opposite direction of y, which means that in fact this transformation is nothing else but a symmetry relative to a symmetry about the x-axis. So each point is mapped into the point with opposite y. And a symmetry, of course, cannot be made into a rotation. No way you can rotate your coordinate frame to get this type of symmetry. This is a different kind of transform, which is characterized by the fact that the determinant of A is equal to minus 1 in this case. Moreover, you remember that we defined our xy coordinate system as a right-handed one. Xy is right-handed, which meant, in our definition, that the shortest rotation from x to y axis is counterclockwise. Counterclockwise. But now, after the symmetry, the coordinate system x prime, y prime, precisely because we got a symmetry with a negative determinant, with the determinant being minus 1, precisely for this reason, it is a left-handed system. Now, the shortest rotation from x prime to y prime is clockwise, which we normally don't do. Okay, so we have clarified the role of the determinant. and the linear transforms, which are, we have already seen, actually rotations and symmetries about an axis. And obviously combinations of them are possible. So it is possible to, for example, first perform a rotation at a certain angle, so to get, let's say, x prime and y prime, and then also then perform a symmetry about this axis or another one. And as you can see, all those linear transformations, which may be complex enough even in a two-dimensional orthogonal cases, they can be expressed as expressed algebraically via multiplication of matrices. So, for example, a composition of a symmetry and a rotation can be expressed as matrix multiplication. One of them standing for a rotation, another one standing for symmetry. And again, the order does matter. Matrix multiplication is not commutative, as we have seen. So it does matter whether we perform a rotation first and then a symmetry, or we perform a symmetry first and then a rotation. Okay, so that should be more or less clear. And why actually we needed this matrix notation very much? Well, in the two-dimensional case, which is, as you can see, in general might be complex enough, even a two-dimensional one, well, we still could probably write these transformations explicitly. But in a three-dimensional case, linear transforms in a three-dimensional case, then the situation becomes so complex that we really need matrix notation in 3D cases. So we'll now consider 3D transforms and their matrices. Okay, so why do we need three-dimensional coordinate transformations? This is very important because our coordinate system in the physical world is three-dimensional. We live in a three-dimensional world, and we need to be able to express coordinates in different coordinate frames. To give you some thought of that, first of all, I will draw up a general three-dimensional coordinate frame. X, Y, Z, and similar to the previous one, I will define this X, Y, Z to be right-handed, now X and Y are not enough, we need to involve Z somehow. So basically it is like this. Consider the XY plane. How we're looking at XY plane in this drawing. We're looking at this plane from above. From above, it means we're looking actually from a positive direction of vector Z. So we're somehow located somehow in a positive Z, here in a point with Z greater than 0, and from that point, we're looking upon our coordinate frame. So it is right-handed if looking from a Z positive, again, a shorter stern probably the shortest term. The shortest turn from x to y is counterclockwise. In this case, x, y, z is right-handed. It would be left-handed, obviously, otherwise. Okay, now let's consider an example of two three-dimensional coordinate systems and how a linear transformation can be defined between them and why we need it. We are working day to day in our daily examples in mechanics and physics with many coordinate systems. So we're on the planet Earth. So let us define a so-called geocentrical or geocentric coordinate system. Okay, so I will try to draw up a globe. XY is the equator plane, equatorial plane. It is the plane of the equator of the Earth. Okay, Z points to the North Pole. The origin of this system is in the center of the Earth. Okay, so this is, excuse my drawing, the northern hemisphere. This is the southern hemisphere. Okay. So we already know that that points to the North Pole. We know what the XY plane is. So in order to define our coordinate system completely, we only need to know where the x-axis points to. So in that case, we introduce the geographic coordinates. So these are obviously meridians. And let's say that x points in the direction of the 0 meridian. So 0 longitude. In general, for any point on the surface of the Earth, initially we assume that it is a sphere. It is not completely true. In general, a much more reasonable model is an ellipsoid, which we'll consider later on. But for the moment, we consider it to be a sphere of some radius r. So for the Earth, the radius is, well, it is variable because it is an ellipsoid in general, not a sphere, but I would say 6,378 kilometers. In fact, it is the equatorial radius. The polar one is smaller, but for the moment, I assume that it is a sphere of the radius equal to the equatorial one. Suppose that there is a point on the surface of the Earth with longitude equal to lambda and latitude equals to phi. So what does it mean? It means that if we draw up a meridian going through this point, then this meridian, when it intersects the equatorial plane, it makes the angle lambda, precisely the longitude, the angle lambda with the zero meridian, which is the Greenwich meridian corresponding to longitude 0. And now, in the plane of this meridian, if we draw up a radius vector of our point from the center of the Earth to the current point on the surface, then this radius vector makes the angle phi with the xy plane. Therefore, let longitude lambda is from 0 degrees to 360 degrees, or obviously in radians it is from 0 to 2 pi. Latitude phi is, the maximum is 90 degrees, the minimum is minus 90 degrees, which corresponds to South Pole. Therefore, it is from minus 90 degrees to plus 90 degrees, or in radians, it is from minus pi over 2. Normally, we would use radians instead, obviously because this is a standard argument of all trigonometric functions, from minus pi over 2 to pi over 2. So, how do we convert our longitude and latitude into this geocentric XYZ rectangular or Cartesian coordinates? That's probably very easy. So first we project our point at latitude phi onto the xy plane. So this is obviously R. We assume that it is a sphere. Therefore, the projection has the length from the origin equal to R cosine phi. Okay, and then this projection can be projected further onto x and y, and we get x equals to R cosine phi cosine lambda, y equals to R cosine phi sine lambda in a similar way, and finally projecting R onto the z axis, the angle between them is pi over 2 minus phi. We see that z is simply R sine phi in this case. And it is very easy to see, obviously, that x squared plus y squared plus z squared equals to R squared. Okay, so this is a connection between geographic longitude and latitude coordinates and the XYZ geocentric coordinate system. But now let us consider something little bit more complex. Okay, I will draw up this globe again, but now along with our geocentric coordinates, we will introduce topocentric coordinates. Topocentric, topos is place in Greek, are coordinates attributed to our local point. So what do we need in our, what do we have in our local point? In our local point, we have some direction to the north, local north, and let it be our y direction. We have some direction to the east, and let it be our x direction. O prime is our origin of this point, and we have also z, the z axis, which is pointing directly upwards. Okay. So what do we do? 1 second, please. A small pause. Okay, so we are drawing up our globe, and on that globe we will point our place as we did. So again, this is the equator. Okay, northern hemisphere. Now this is our meridian at longitude lambda. That's our latitude. So again, x, y, and z are geocentric coordinates. And now what are our topocentric coordinates? They are here. So let's have a look. So what is the z-axis? As we said, z is, let me call them x prime, actually y prime, z prime. Z prime is pointing straight into the zenith, so up. What is up? Up is a continuation, if it is a sphere, so up is orthogonal to the surface of the sphere. So that's our z prime, okay? What is y prime in this case? Y prime is pointing to the local north, and therefore it is tangential to the meridian and in our local point here. So that's our y prime, okay? And what is x prime? X prime is pointing to the east, local east, and it is orthogonal to y prime. Okay, so what we want formulas providing connections between x prime, y prime, z prime, and x, y, z in this case. So connecting the topocentric coordinate system and geocentric coordinate system. First of all, please note that they have different origins. So the geocentric has an origin in the center of the Earth, O, and the topocentric one in O prime on the surface of the Earth. So what we will do in that case, we will first of all do a matrix of linear transforms and then also change of the origin. Change of the origin is called translation in order to connect the coordinate systems. In this case, it is a little bit more convenient, I believe, to work backwards. So, suppose for the moment, suppose that the origins are the same. And this would allow us to more easily derive the general linear part of our transformation. And then we'll handle translation later, when we really say that O is not the same as O prime. Okay, so let us consider what is the vector. It's easier to start with that prime. So again, we would have I, J, and K vectors here, and normal vectors of the old system, and I prime, J prime, K prime of our topocentric system. The easiest thing is to start with K prime, because K prime is just a unit vector in the direction of our radius vector of this point. And this radius vector we have already obtained. So we can say that K prime is a vector. Now it is a unit one. It is like XYZ vector here, which is a radius vector, but without the multiple R, because we are interested in a unit vector. So it is cosine phi cosine lambda, cosine phi sine lambda, sine phi. Okay, so we know K prime in the original frame, or we can obviously say it is cosine phi cosine lambda I plus cosine phi sine lambda j plus sine phi k. Okay, now what is the vector, for example, j prime? J prime is a tangential vector which points to the north. So basically we can project this vector onto the xy plane, and we'll see that it is actually pointing into the opposite direction because it is pointing to the north, to its projection to the radius vector. So its projection to the xy plane, j prime, its projection to the xy plane is, there is, that's phi angle between them. But you see, we need to be very careful here, whether it is sine or cosine of phi. When phi is 0, the way the j prime vector is pointing straight upwards, and therefore its projection to the xy plane is 0. So it is sine phi. Okay. Then when it is projected to this plane with the sign, it is pointing to the opposite direction than the projection of the radius vector. Therefore, we put minus sine phi here. And then it is again cosine lambda projection to x, sine lambda projection to y, and obviously in that case it has a cosine phi proportional projection to z, which plus or minus. Normally you see when phi is positive, it has a positive projection to z, therefore it is cosine phi. So we got j prime. By the way, we must immediately check, obviously it is normalized to 1, we must immediately check that this vector is orthogonal j prime to k prime. So let's compute k prime times j prime equals to minus sine phi cosine phi cosine squared lambda minus again sine phi cosine phi sine squared lambda plus cosine phi sine phi. Obviously, cosine squared lambda, sine squared lambda result in 1, and we have indeed 0. So yes, k prime and j prime are orthogonal to each other. So we hopefully obtain j prime correctly in this case. Now, let us compute the I prime vector. So what is I prime? I prime is a vector pointing to the east, and although it is not immediately obvious, this vector is horizontal. If it is pointing to the east, then it is parallel to the equatorial plane. Therefore, its projection onto xy plane is 1 in length. Therefore, its projection onto z is 0. So we already know that. Projection onto x1 is 1, and you see that this vector is orthogonal to our longitudinal projection. Therefore, its angle with the x is pi over 2 plus lambda. Therefore, it is cosine pi over 2 plus lambda, and with okay, and its angle with y is lambda itself. Therefore, we would have minus sine lambda, cosine lambda, and 0 in this case. Okay, let us check the orthogonality. I prime times k prime, for example, is minus cosine phi sine lambda cosine lambda plus just a second, yes, plus cosine phi sine lambda cosine lambda 0. Okay, I prime times j prime, the dot product, checking orthogonality, is sine plus sine phi cosine lambda sine lambda minus sine phi sine lambda cosine lambda and 0. Therefore, 0. Okay, so we have now constructed our frame k prime, I prime, j prime, k prime, expressed in the original coordinates x, y, and z. Okay, and from this we can compute both actually forward and direct transformations between the coordinate systems. So how do we do this? Again, by using, it's easy to do this way to avoid any confusion.